Good evening, young people. It's Mrs. Rains. I'm going to talk a little bit about Coulombs Law to help support your understanding of periodic trends in the correct way, because Coulombs Law explains what's happening with the trends. So here we go. You already know what Coulombs Law means. So let's look at some charges and see if we can figure out what's going on here. So I have one positive charge and a second positive charge. So I've got two like-charged particles. What do you know happens? Yeah, you know that they're going to be repelled from one another. They're going to be pushed away from one another. So that makes complete and total sense to us, right? Okay, what happens to these particles? A little different, right? So they are going to be attracted to one another. So they're going to want to come together to one another. So we know that. And that's basically Coulomb's law in a nutshell. But we want to get a little deeper with it because we want to understand the factors that are affecting Coulomb's law, and then understand the atomical structure and how that affects the factors. So that's where we're headed. So Coulomb's law helps us describe the forces that bind electrons to an atomic nucleus. Sorry, you probably can't see the word bind there, but bind electrons to the nucleus. So basically, we're talking about forces. Coulomb's law is a description of force. So we've seen this. We've seen positive and negative. They're going to come together. The force of that, we can calculate it. The force of two particles that are repelling from one another, whether they're positive and positive or negative and negative, it's the same idea. And you can see we have some things. We have force, and we have Q, and we have R. So you can see the force of this is going from 2 to 1 and going from 1 to 2. We can see that they're labeled and all wonderful. But ultimately, force is just equal to K, some constant, and the constant is only there because of substance, a media. So as long as you're in the same substance, it doesn't matter. Usually we're in air, so K is constant. It doesn't matter. Q1 and Q2 are basically the charges on either one of the particles, okay? And then R squared, R is the distance. R is the distance. R means the distance from the center of the nucleus to the outer edge of the atom, where the electrons would be, the last part of the electrons. So based on Coulomb's law, the force between two particles is proportional to the magnitude of the two charges and inversely proportional to the square of the distance. What we mean by inversely proportional is on the bottom, and it's squared. So it's an inverse square proportion between the distance, and the magnitude of the two charges are multiplied by each other, so they're proportional to that. So we see that we have that information right there. So let's look at this and see what we can come up with, okay? So here we go. I'm going to start writing a little bit. I like purple today. I don't know why. I've been kind of feeding for purple. So what if I had a positive charge and a negative charge, and they were 1 away from each other? What would be the force? Well, the force would be plus 1 times a minus 1 divided by 1 squared, which would equal minus 1. What if I had two positive charges? Positive 1 times positive 1, and they were 1 away from each other. Oh, that'd be a plus 1. Okay. What if I had two negative charges? So negative 1 times a negative 1 divided by 1 squared is equal to a positive 1. Something interesting that I'm seeing here. I've got a negative sign, I've got a positive sign, and I got a positive sign. What does that mean? Well, this means that the force is a vector quantity, meaning that it's telling direction. So in reality, that positive and negative sign is telling us the direction that the charges are going to be going. So we have to kind of make sure we understand that. So negative means that they're attractive. When we have a negative force in Coulomb's law, it's an attractive force. It means those two particles are going to come together. When we have a positive force, that means they are repulsive forces. They are going to fly apart. The direction is determined by the charge. So the charge is the direction. The magnitude of the charge is the amount of the force. Are we good so far? All right, so let's try another one here. So let's go back to our original assumption that we have a positive charge and a negative charge, because that's what we have in our atoms, and they're 1 away from each other. And we know that that's a -1 force. But what would happen if I increase the distance? have the same kinds of charges, but instead I'm 2 away from one another. What does that give me? Positive 1 times negative 1 is negative 1 divided by 2 squared. Well, that's negative 1/4 or negative 0.25. So what happens when I get further away from that nucleus? The further away from the nucleus I get, the lower the force gets. So as the radius goes up, the force goes down. So we've got an indirect relationship there with radius and force. And we can see that that's the inverse. Remember the inverse proportionality. So we kind of see these numbers. Now I want you to look at another situation. Let's change something else. Let's change the number of protons that we have. So if I have 5 protons and 1 electron that I'm looking at, and it's 1 away, what's the charge? Yeah, it's -5. Very good. And if I have the same 5 protons and the same electron, but they are 2 away, what's the force? Okay, yeah, it's negative still because they're going to attract. -5/4 or negative 1.25. So what do we know here? What happens? Well, every single time when I increase the amount of protons, I've increased the amount of the force. This used to be a -1, this used to be a negative 0.25, so they've increased overall. But which one of these two forces is bigger? Be really careful. Don't look at this as a number line situation. Look at the magnitude of the number. Remember, the negative and positive means that I'm attractive. Yeah, so the 5 is bigger. So this is the bigger force. That's the bigger force overall. So we have to kind of remember that when we're looking at all of this, that the sign is telling us whether it's attracting or repulsing, and the magnitude of the charge is telling us how much that is. Now, I'm not really going to make you ever calculate with this. So what I'm really trying to get you to understand is the relationships between Q and R and the force. Very much like we were trying to develop the relationships for force and mass, and the Q is equal to M times C times delta T. We're trying to develop those same relationships. So let's keep going a little further. So there are three factors that affect three factors of the atomic structure that are affecting Coulombs law, or that Coulombs law explains. I should be more clear about there. The first one is electrons can be found in energy levels orbiting around the nucleus. Bohr actually originally discovered this. Now it was kind of enhanced when the quantum model came along, but Bohr discovered this first. And what this says to us is that all electrons orbit the nucleus of an atom in energy levels from it should be lowest to highest. I'm sorry. These should be switched lowest to highest. Okay, lowest to highest. Sorry about that. And so what do we know? We know that electrons found in higher energy levels are further from the nucleus. Therefore, the force holding those electrons into the nucleus would be weaker according to Coulombs law. Why? Because if I increase the distance, I decrease the force. So as I'm going from the nucleus here to energy level 1, 2, 3, 4, 5, 6, and 7, these electrons out here are further away from the nucleus than these electrons in here. So Coulombs law explains that very well and why that happens, okay? The next factor, the charge on the nucleus is equal to the number of protons found in the nucleus. That is, the number of protons is equal to Z, the atomic number. We already knew that. What does that have to do with anything? Well, as I add more protons to the nucleus, the amount of the charge pulling on any electron is increased, causing the force pulling on that electron to increase. So what are we saying? We're saying when Q goes up, I'm sorry, that's not Q. That's not a good Q. Okay. When Q goes up, the force goes up. We saw that earlier. Remember, when Q went up, both of those forces went up. So we kind of get that too. There is another application of what Coulombs law tells us about the structure of the atom. Now, there's something that kind of gets in the way of this nuclear charge, and that is the shielding effect. And the shielding effect says electrons found in the inner orbits shield electrons found in the outer orbits from the pull of the charge on all of the protons. So because all of the protons are not pulling on the electrons, the force will decrease some. So that gets a little weird. So let's explain that a little bit further, okay? So the effective nuclear charge is what we're talking about. How much of that nucleus is pulling on those outer electrons out there? So in many atoms, electrons are attracted to the nucleus and repelled by other electrons. It's amazing, right? Well, let's say negative, negative, they're being repelled. Positive, negative, they're being attracted. So we have to deal with this in a way that makes sense. So what we see here is that the nuclear charge depends upon both of these things. And part of it is that you have electrons that are on the inside that are trying to repel the electrons on the outside to keep those protons to themselves. And one electron and one proton cancel each other out is what we understand. So what we have is this idea that we can calculate something called Z effective. So to find the force of the proton effect, so to find the Q of the proton correctly, I have to calculate Z effective. So Z effective is equal to Z minus S. Remember, Z is the atomic number, which equals the number of protons. But we need to know what S is. S is the number of inner orbited electrons. So any electron that is not in the valence orbit or the outer orbit is considered an inner orbit electron. And so we have to consider those. So let's look at an example. Calculating Z effective here. Here I have an atom of phosphorus. How do I know it's phosphorus? Well, I have 15 protons. So I know to calculate Z effective that I have to have Z. Z is the number of protons, which is 15. So S, what is S? Well, let's look here. I see 2 electrons, one here and one here on the inner shell. I see 2, 4, 6, 8 electrons there. That's another inner shell. So those 2 shells, this shell and this shell, are considered inner, while this shell is considered an outer shell. How many electrons do we have? I see 1, 2, 3, 4, and 5. So what does that mean? Well, that means S, the number of inner orbital electrons, is 2 plus 8, or 10. So Z effective is 15 minus 10, or 5. So what 5 represents is the amount that the protons are pulling on that outer electron. We can't give it more. We can't say 15 because 10 of those protons are being shielded by the 10 electrons that are inside there. Okay? So this is where we're going to end that. Hopefully this helps you with your process this weekend with answering those questions. Remember, don't be too specific about answering those questions. Be a little less specific. Be a little more global. Think about the ideas of distance. Think about the ideas of amount of charge and how those are affecting force. Remember, as charge goes up, force goes up. As charge goes down, force goes down. As distance goes up, force goes down. It's inverse. As distance goes down, force goes up. So keep that in mind when you're trying to figure out what you're doing here. Thank you.